All right, so welcome back. We'll start right away with a question on, I think it's on the Yarn quiz. I have the feeling that, so somebody's asking that there was a Yarn quiz released, but we dropped the part on Yarn. What's your intent, Wenxi? I mean, it seems to me that the quiz is simple enough that you can almost answer it with just what I told you today. So it still makes sense, right?
I didn't make the quiz. I think some other TAs made it. So either we can drop it and reducing the score needed to get a bonus, or we can continue it if.
Okay, so let's say do it if you want, but it doesn't count to the bonus points. We'll still have 25 bonus points, but we'll just redistribute it on the other weeks, right? So do it if you want. It's an optional, ungraded quiz exercise. How does that sound, Wenxi?
Oh, yes, that's good.
All right, so just take it as an exercise that doesn't count.
Yeah.
Okay. And we'll still have, so the plan is still for the graded ones, there will be 25 in total, and every one of these gives you 0.01 points. Okay. But it makes sense because I told you that Yarn is dropped. So if Yarn is dropped, then you shouldn't have to be graded on Yarn. Okay. Very good. All right. So this is what Spark looks like in a shell or in a Jupyter notebook. You create your transformations, and then you have an action that outputs the results. Well, you know, when I was a kid, we didn't have a lot of TV channels. We had, you know, antennas on the roof, and then there were maybe 1, 2, 3 channels available. And then came the cable subscriptions, and even with the satellites, the satellite dish, suddenly you had 200 or even 500 different TV channels. Well, what's going on today is pretty much that. We had 2 channels with MapReduce, that was Map and Reduce, and now we suddenly have a cable subscription of transformations that we now have 100 of them. That's pretty much what's happening. And so I just need to go through them, but these are not, of course, TV channels, these are transformations, but it's just a restaurant menu. In the end. So here are the new TV channels that you have in order to do your transformations. So I'm going to start with the easy ones that take an RDD, return an RDD, right? Okay, here's one. This is the filter transformation. What does it do? It takes an RDD and returns some of the values, but not all. So you just need to supply a function that says yes or no, right, to each value. So this says, no, we don't have it. Yes, yes, no, yes, no, 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 yes, yes. And you get these values in the output RDD, right? So this is called filter. The order matters, right? So there is an order in the values there, and there is also an order in the values there, right? But it's basically an extraction of just those that are left by the filtering function. So this is a filter transformation. This is a new channel, right? We didn't have it with MapReduce. All right. Okay, then there is a map function. What does it do? Well, it's a mapping function that says for this input value, produce this output value, right? So then it just applies the map function individually to every value in the output and creates exactly one value in the output, right? So you might think, okay, this is the MapReduce map. Not exactly. In fact, the MapReduce map would be closer to this one right there. That's called the flatMap. Let me explain the difference. So what's going to happen with a flatMap is that the function here takes one value and it outputs 0, 1, or more output values, right? And we have the bell, quarter past. Okay. Why is it called flatMap? Because when I have this value there and I call the function, in that case, that gives me 4 values, but I flatten everything back, right? In the output, I just flatten everything. So these 4 appear next to the other ones, right? So this is why it's called flat map. In that case, if you had, you can really only produce one value here. Of course, you could package and put 4 values inside as a single big value if you put it in a box, but then they would be grouped together in there as a single output value. But here it's a flat map. And so the reason I'm saying that this is actually what corresponds to the MapReduce map is that you remember that the map function in MapReduce can produce 0, 1, or more intermediate key value pairs. So in fact, it's the flat map transformation that corresponds to what we were doing in MapReduce. Okay, so this is flatMap. So we know filter, map, flatMap. Here's another one. It's called distinct. What distinct does is that it checks for equality, or for, if two values are the same, and it's only going to output one value for all of them that was the same. So here we have blue, blue, and blue. It's only outputting one blue. Here we have green and green. It's only outputting one green. So it's really just a duplicate elimination that's going on there, right? So this is called distinct. Observe that here the structure is rather parallel here, here, and here. And here it looks more like a spaghetti, right? Just a remark, I'll come back on that. Here's another one. It's called sample. As you might have guessed, what it does is that it's throwing dice every time for every value, and either you keep it or you don't keep it, but it's just random. So you need to provide some input to trigger the probabilities, right? This is the sort of things you learn in probability lectures or cryptography lectures, right? How to trigger a probability or a random draw. But basically, we just pick at random values in there and output them. So the fraction is, for example, let's keep 10%. Let's pick 10% of these values randomly, and this is what I get right there. So this is the sample transformation. Okay. So of course, I'm not giving you all of them. Like I said, it's like a cable subscription. You have so many channels that you don't even know them all by heart, right? But I gave you some of them. Do we have a question?
If we have flatMap, why would we use map?
Oh, because in some cases, you still want to keep track that what came from each value in there. In the flatMap, you lose the information that these four came from the same value, because when you flatten, you just have everything back on the same level. So you don't have a boundary here or here. In the map, you can basically squeeze these four inside a box, there, and then you know that they belonged together where that came from. So this is the main difference. You basically lose information by flattening right there on the provenance.
Another question is that, is sample like filter but random?
Yeah, that's pretty much what it is. You could actually, if you want, write a filter function with a random pick, and that would pretty much be the same, right? Of course, be careful, because the theory of pseudo-randomness and randomness generation is not that trivial, but the short answer is yes, absolutely, this is exactly what sample is. It's like filter, except that it's a random draw instead of a deterministic function.
Why are there two blue blocks on slide 50? Why are the blue block but not transformed on the same blue block?
Yeah. Probably it's a problem with the colors. When you copy paste in PowerPoint, sometimes the colors get. I will fix that color. It should, of course, be a different color, right? So it's probably a different shade. I'll put some yellow or red or whatever other color I will find. Yes, you're absolutely right. It shouldn't be the same color. Right? Okay. Okay, so you see, this is the appetizer. These are a few of the transformations that you have in Spark. Let's continue, and let's look at something also cool. You also have transformations that involve two RDDs, meaning that you have one on the left, one on the right, and then you combine them into a single RDD. For example, you can do the union. So you have one RDD here, union this other RDD here, and what it does is just puts them next to each other. Of course, here, you're going to tell me the terminology. A union normally is about sets, but here it's actually ordered, and it's a list of values. So maybe it should have been called concatenate. Maybe concatenate would have been more appropriate. But it's called union, right? So it's the union of this and this, but actually, it preserves the order. So it's first the values from the left and then the values from the right. Okay, it comes down in the relational algebra to set versus bag, right, of tuple. It's very similar. Okay, then there is the intersection, where we only output the values that are on the left and that are on the right, right? So blue is on the left and on the right, green is on the left and on the right, but here I will fix the colors right there. Black here is not on the right, Red is here, but is not on the right. And I will make sure to fix these colors that probably also got information lost along the way. Okay, but this is pretty much the intersection, right? We just keep everything that is on both sides. And the last one is subtract, which takes all the values that are in there and that are not on the right. So this is the subtraction, right? So gray here is here, but it's not on the right. Orange here is on the right, so we don't copy it over. Purple is not on the right, so we copy it over. Blue is on the right. Green is on the right, so we don't copy it over. That's subtract. It might not have escaped you that these three here, union, intersection, subtract, are pretty much the same ones you have in SQL and with relational tables as well. That's actually not a coincidence, because as you can imagine, the values right there could also be table rows and records, right? But I'll come back to that. But anyway, union, intersection, subtract. Then we have the Cartesian product, meaning that I have an RDD here and an RDD there, and I'm building an RDD with all possible pairs that you can obtain with the first in the pair coming from here, the second part of the pair coming from there. So these are pairs of values. But as I told you, an RDD in Spark is a collection of whatever. So a collection of whatever can also be a collection of pairs, right? This is fine. So I have here a collection of pairs coming from here and from here, all right? Careful with this. Imagine that you have a billion values in there, and you have a billion values in there. I can only let you imagine the catastrophe that's going to happen to your cluster if you try to compute the Cartesian product with a billion and a billion, right?
Yeah.
Yes?
We have a question on the last slide, slide 55. Yep. As red is only in the second block, does that mean it only takes the value from the first block?
Yeah, it's not symmetric. So there is a distinction between left and right here. And if you did the opposite, the other way around, the result would be different, right? So indeed, the left here is not treated the same as the right, unlike intersection and union that are a bit more symmetrical, all right? Wonderful. Very good. And please continue to ask questions, right? That's exactly the point here. All right. So I give you the warning, be careful, billion, that's 10 to the power of 18. You're looking at a quintillion values in there, you're going to crash your cluster. So this here, use parsimoniously. Right. Okay. So these are some of the transformations. Okay. But the transformations, they don't do anything until you call an action, right? So let's look at the actions then. What do we have in the actions menu? Well, the first action is collect. Collect is actually the identity function. It just takes exactly the same thing, but it's called an action. What's going to happen is that all of that was on your cluster. It's going to download everything from all the machines in your cluster and build locally on your laptop or on the machine that you're actually sitting with your Shell or Jupyter notebooks. It's going to accumulate these values downloaded from the cluster into a local list in your memory. As you can imagine, if you have a billion values in there, you're going to crash the whole thing. It only works if you know that this RDD actually is rather small. Maybe you know that there's only 100 values, then you call collect, and then you get your 100 values nicely on your screen, on your computer screen. So you need to know, you need to be aware of what you're doing, right? Again, if you have a billion values and you try to collect, that's probably going to crash your system. Okay, then you have count. Count will not crash, for sure, because count is just one single value, right? So count is, of course, it's going to do it in parallel, just like the Pokemons, right? So it's going to count in parallel in the cluster, and it's going to tell you how many values there are in this RDD, in that case, 22. Another one is count by value. Oh, we've seen that one. We've seen that one in the sample that I gave you earlier. So in that case, if I give this RDD right there, that might have multiple values repeated, right? This is going to tell me, okay, 12 blues, 4 oranges, and 6 greens, right? So this is count by value. These are key value pairs, blue 12, orange 4, green 6, key value pairs. But if you know that there are not so many distinct values in there, again, this is small enough that you can just download it and have it locally on your machine. So this is count by value. If all the values here are unique and there's a billion of them, again, that's going to crash your system, right? So be careful when you when you do this. Okay. Take is another one. It's only taking the first values. So imagine you have 1 billion values in that RDD and you only want the first 4. It's like peeking at the first values. So you say take 4, and it's only going to download the first 4 values. Right? So this is sure, no, it's not going to crash because you control the number of values that you pick. So this is if you don't know how many there are, then you should use take or count if you want to check how many there are. But this is safe to do take. Top is the opposite of take. So take would be the first ones, top is going to be the last 4 ones, right? And of course, you can change that number if you don't like it. And take sample is just like the sample of the that we saw earlier, but take sample is an action. Sample was a transformation, take sample is an action. So again, the difference is that it actually downloads these values that it sampled to your machine, to your local machine. So it's an action. So this here will be in your Jupyter notebook. All right, so you specify the number that you want. Then you have reduce. Reduce, surprise, surprise, that's actually shouldn't surprise you very much. We were missing that one. Reduce is just going to apply some binary operator on these values. For example, imagine you have 1 billion integers and you use plus. This is going to compute the sum of these billion integers and return that to you. As you might imagine, it's a good idea if this operation is commutative and associative. That's exactly pretty much like the combine operation, because then it can be computed efficiently and in parallel and in batches, right? So commutative associative is good. So plus, min, max, count, that all works. Average, no. Average, as we saw, is not associative. If you compute the averages and you compute them in different ways, the results will be different. Okay. But just like map, this reduce is not exactly the same reduce as in MapReduce. I'll show you the one that corresponds to the reduce in MapReduce. Why is that not the same? Because we work with pairs in MapReduce, but here these are not pairs, these are just single values, right? So this is why be careful, the names here might not be exactly the same as in MapReduce. Okay, so talking about pairs, since we are talking about MapReduce, it would be nice if we would also have a few transformations and actions on the menu that actually handle pairs, right? So let's look into them. Do we have a question?
Yes. What is the difference between mean and average?
Mean is the minimum. It's commutative and associative. You can swap the values and you can also compute it in any order you want. Average is not associative. Imagine you compute the average between 1, 1, and 2. You start with 1 and 1, average 1, and then 1 and 2, 1.5. But if you compute it in a different way, you start with 1 and 2 that gives you 1.5, and then 1 and 1.5 gives you 125. So you see, it's not associative. You cannot compute the average in any order you want, right? That's what I mean here.
Another question.
Max sum is safe. Yeah, go ahead.
If we apply take, do we always take the values in the beginning? And is there an application to take values in the middle?
No, it doesn't do that, at least not efficiently. So the way you would take the values in the middle, you could, if it's not too much in the middle. For example, if you want these 4, then you would have to take the 8 and then manually remove the first 4. But if you want the one that are exactly in the middle, I can tell you how you will do that. There is a transformation called zip with index. Zip with index is going to add numbers 1, 2, 3, 4, 5, 6, 7. So it's going to basically annotate all of them with increasing integers. So you need to do zip with index, and then you use the filter transformation, selecting the pairs, because if you zip with index, you get a pair with a value and an integer. Then you filter the integers that are the ones you want, and then you collect. That's the way you would do that. But there is no direct way of doing that. You need to do it with these 3 steps explicitly. Did I answer your question? All right. So again, you can do it. It's not going to be efficient.
What is the type of data contained in the box?
Anything. It can be integers, it can be colors, it can be JSON objects, it can be XML nodes, it can be database rows, it can also be the row of a table. It can be strings, it can be pairs, it can be pairs with a string and an integer, it can be dates, it can absolutely be anything. Did I answer your question? Yeah, wonderful. That's the beauty of it, right? It can be anything. You can put whatever you want in there. Okay. Any other questions? Okay, let's continue then. Okay. Oh, another question?
If data can be anything, I assume that we need to define the transformation to parse the data accordingly. And we may not simply be able to use transformations off the shelf.
Yep, exactly. If you have exotic values, then you need more work. However, it turns out that, for example, let me take this example, filter. Imagine that these are JSON values, and you want to filter based on a specific key of that JSON object doing anything. Where is all that going to happen? Well, it's all going to happen in your function right there. So your function is going to take a JSON object and return something. But the filter transformation here is actually not restricted to any specific type in there, right? For those of you who heard of that in programming languages, it's called templates. It basically means that there is no, the type of the filter function is not specified in advance. It will be whatever the type of your function is. And this is here that you can put a JSON value, a date, or whatever, but filter just doesn't care. That's how it works. But of course, if you have JSON or something, you need to do it yourself to parse it and do whatever with. But we'll see in the future. Of course, in the coming weeks, I'll show you easier ways, right? But with this status quo, it's not aware of JSON, and all the work is in you. You have to take care of that.
So the transformations and actions are computed again in batches?
Yes, I will come back to that in the second part of the lecture, because right now I'm talking on the logical level, right? I'm talking on the high level of abstraction. And as you can imagine, I'm reserving the physical implementation and the architecture for the second part. And then you guessed correctly, it's exactly going to be batches and parallelism. Right? You will not even be surprised because it will just look like MapReduce. Okay. Are there any questions left? Okay, let me continue and don't hesitate to interrupt me if you have any more questions. Okay, so let's look at the pairs. So it can be anything, so it can be pairs. And it turns out that there are specific transformations for pairs. For example, imagine we know that we have an RDD of pairs, so key value every time. There is a transformation called keys, and surprise, surprise, what does that transformation do? It extracts the key from every pair, right? So it takes just the key, just the key, just the key, and then you output the keys, right? Of course, there's the other one that's called surprise, surprise values. And this one takes the value from every pair and gives you the values, right? Then there is reduce by key. Now, this is the reduce of MapReduce. This is the reduce of MapReduce, right? Because here we are in the MapReduce territory, right? We have key value pairs. We are grouping together the keys that are the same. So orange, orange. We have a reduce function. And for every distinct key, we are applying that function to get an output with that key and that result. So this here is the MapReduce reduce function, right? So flatMap corresponds to the MapReduce map, and reduce by key corresponds to the MapReduce reduce. All right. So you see now that it's more generic than MapReduce because it doesn't just have two transformations; it has 100 of them. Here's another one. Group by key. Okay, what's going on in here? This is very interesting. So I'm grouping the key values that have the same key. And now I'm kind of packaging together or squeezing together the values here, 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 and here. I'm packaging them together. Well, you can do it in Python, that's a list or an array or whatever, but we just package them together. So we have the key and all the values together. This is called group by key. Right? So this is where we are in the NoSQL territory, where the values can be complex. We can have structured values. It doesn't have to be just integers or strings. We called it atomic, right? Remember that first normal form I told you about. Here we can absolutely have nested structures. For example, it could be a JSON object with an array here, right? Okay, group by key. Now we have sort by key. Okay, I told you this is ordered, right? But maybe here it's just unsorted. So you just specify the sorting algorithm, so a comparison operator. And now it's going to nicely sort the key values pair looking at the key, right? Then we have map values. Map values is going to map every key value to a key value that has the same key. So it doesn't touch the keys. Key is the same, but it's going to apply a map function just to the value. So it's very similar to map, but it's applying it to the value in every key value pair, right? You just need to specify the function. Then you have join. What is join? Now, this is sounding a lot more like relational algebra, right? But it's not a coincidence. What is join doing? Well, join is trying to map, map is not the right word, pedagogically, to put together the keys that are the same. For example, here, this and this, right? So here, this is going to be joined together by the same key here. And here I put the value from the left and the value from the right. But there is also this key that appears again here. So I also need to join this one with that one. If you think that these are database records and we are joining, it's a theta join where we are joining this attribute with this attribute, then probably that suddenly makes a lot of sense to you, because this is really what's happening also with relational table when you join them, right? So you have the common attribute on which you join if it's a natural join, and then you have part of the columns that come from the left and part of the columns that come from the right. But this is here, it's just more generic with any values. It doesn't even have to be table rows, right? So this is what the join is doing. It's trying to put in combination all the keys that are the same, and then one from the left, one from the right in all possible combinations right there. So you see another one is this joined with this. So this is here, there's only one. So this is the key, and then from the left and from the right, this is what you find right there. Okay. So this is better than the Cartesian product, as you can imagine. Yeah.
No question. If we have multiple keys, do we have to specify the keys, or is mapping it a new value to all the different keys?
All the combinations. If you have 6 times the key here and 5 times the keys there, then you're going to have 30 times the key in there with all possible combinations. It's basically the Cartesian product within the key, if you want to put it that way. Right? Did it answer your question? On the map values? Yeah.
He meant on the map values.
Yeah. Let me think. So you're asking, what if there's multiple times the same key, right? Then indeed, you're just applying every time to each one of them. Here, you don't really care if the keys are the same or not. It doesn't change anything in there. Yeah. Exactly, you're not specifying the key. You don't care about the key in there. You just don't touch it. The key remains.
Yeah. In general, do keys have to be atomic?
That's a good question. It's a very good question. We should check. I think if you really want your key not to be atomic, you might be able to squeeze that, to squeeze some JSON object in a key. That's a good exercise. Can you take a note, Wenxi? We're going to look into that.
Sure.
I think the interface of the key might be generic enough that you can even squeeze something that's not atomic in there. It's possible. I'm not saying you should, of course. Just because you can doesn't mean you should, but it might actually be possible. But again, I don't recommend that. Typically, if you have key values, then it makes more sense that the key is atomic for at least 99% of the use cases. Okay. Any other questions? me continue. Then we have subtract by key. That is just eliminating all the key values if the key is not there, right? If the key is not in the right. So it's just like subtract, but only looking at the keys, right? In that case, there's only this one that survives because these ones do exist here and here, orange and blue exist. So this gets removed and this gets kept, right? Count by key. Careful, this is an action, not a transformation, right? I put in that's a transformation. Here it's an action. Count by key will actually download the keys with the keys together with their aggregated value, right? It's an action. So here you have 6 blue, 1 green, and 4 orange, right? So how do you know if it's action or transformation? Well, you just need to look at the documentation or learn it, right? But be careful because that's not the same. So count by value is an action, count by key is an action, yeah. Okay, but you know the difference now between transformation and action, right? So you know what the difference, what it means. Okay, then we have an action that's lookup. Imagine you have a very large collection of key values and you're looking specifically for whatever value is associated with the orange key. And that answers here black, that's what's right there. All right, so this is a lookup. Of course, that only makes sense if the keys are diverse, right? If it will not work if you have like 100,000 times the same key, right? But if you know that every key is unique, then of course, that's gonna give you here the unique value. Okay, that's the menu. These are your 200 TV channels that you got with your cable subscription, right? So these are all the transformations. It's not even exhaustive, right? I didn't even show you everything. There are many, 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 many more. And you can use them to build your query in Spark and construct your outputs, right? Do we have any questions?
No, not yet.
Okay. So now let me plug it back with MapReduce. What is the difference with MapReduce? Give me the 3 differences with MapReduce on the chat or in the lecture hall. How can you define MapReduce as a specific case of Spark? 1. Anybody? 3 differences between MapReduce and Spark.
Use of key values.
Yep, in MapReduce, you must have key values in your collection. That's the first difference. The second one, very good.
On Spark, we can have multiple transformations.
Yes, exactly. You can have a generic DAG, a generic directly acyclic graph, as opposed to just the 2 faces of MapReduce. And the third one, maybe it goes along to what you've just said, right? The other one is in MapReduce, there's only map and reduce. There's only these 2, as opposed to 100 possible transformations with Spark. All right, so you see, now MapReduce has just become a specific subset of Spark. Spark is more generic, bigger, better, next generation. Right? And of course, you can imagine like this is why everybody is using Spark now. And there's not many people who are directly using MapReduce anymore. All right, and by the way, as I should mention, probably some of the transformations might have felt like the relational algebra. You might have felt like, okay, this looks like a projection, this looks like a selection, this looks like an order by, this looks like a group by. You're not wrong about that, because in fact, Spark can be used as a physical layer on top of which you can implement SQL, right? But I'll come back to that. All right, so as promised, because one of you asked, do we have batches and do we have parallelism? The answer is yes. So let me now show a bit to you the physical layer. We have a few minutes left. All right. So let's take this transformation. In that case, it's the map transformation, right? You should have noticed here that the pattern is kind of regular here. It's all going top down like this. And it's very tempting to, say, okay, that kind of can be done in parallel, right? So what I can do is say, okay, here's a task with just these three. Here's another task with these three. Here's another task with task with these three, and here's another task with these two. Right? So for this specific kind of transformation, you can indeed create tasks, and then you can execute it in parallel. So you can basically separate it in tasks. By default, if the RDD here was directly created from HDFS, probably you want to say, okay, the tasks are going to be assigned to HDFS blocks, right? So this comes from an HDFS blocks, this is another HDFS blocks, this is another HDFS block, and this is another HDFS block. Modulo, what I told you, that one value, the last value here, might be spread across two blocks, right? But this is not a problem, just a remote read, right? But most of the values will come from within the block that you can directly read from the machine. Anyway, one task for each ADFS block in the input. Okay, so logical, physical. Logically, we have an RDD, the first one, RDD1, we transform it to an RDD2. Physically, what's going to happen is that in case we have 4 machines, and each machine, in that case, executes one task. So this machine takes care of the first 3, this machine the next 3, this machine the next 3, this machine the next 2. Right. Again, this is the logical view, high level. This is the physical view. If you actually look at what's happening in the cluster. Of course, the user doesn't see that. This is all hidden from the user. Right. So in that case, I had only one task per machine. In general, as you can imagine, one machine can have several tasks, right? So maybe this machine has 2 tasks, this machine is executing 3, this one has 2, and this one has 4. This is no different than MapReduce, because again, this is sequential, right? This machine here does first task 1 and then task 5. This machine does first task 2. When it's done with task 2, it does task 6. And when it's done with task 6 is does like the tongue twisters in what I'm telling you, task 9, right? Okay. What's actually happening in there is that they all start with 1, 2, 3, 4, and then executor 1 is done, then it gets task 5, then executor 2 is done, the task 6, 7, 8, 9, 10, 11. So you see they are just given in the order in which they are finished, right? Whenever one is finished, they just get the next task. Okay. Now, even more precise, and here this is new because here it looks a bit like MapReduce for now. But here, even more precise, you might know that on the same machine, you might have multiple cores. So maybe you had here one machine that has core 1 and core 2. So in that case, core 1, it's like a slot, will have 2 tasks. Core 2 will have 3 tasks. Core 1 will have 2 tasks, and core 2 will have 4 tasks, right? Okay, so far so good, right? You might have noticed that here I didn't write machine, I wrote executor. Why did I write executor? Well, it's just the Spark name executor for what we call the container earlier. Remember with Yarn, the container? So on the same physical machine, you can have multiple containers. This is one container that's called an executor in Spark. So maybe it has 2 cores and 10 gigabytes of memory, right? And this might be on the same machine, but it has 2 other cores and then again, 10 gigabytes of memory. Right? But you see that on every core, we just execute tasks in parallel like this, all right? Okay, so this is for one transformation, right? So I hope it's clear that we are batch processing just like in MapReduce because we are doing it in batches, right? But we are also doing it in parallel because these 4 cores execute it all in parallel. It's within a core that it's not in parallel. Within a core, it's sequential. Okay. So next, what happens if I have not one transformation, but let's say 3 transformations? Maybe this is a filter, and this is a map, and this is a flat map. So how do I implement that physically? So maybe like this, right? So I have 4 machines that do the first transformation in parallel, then there's a bit of shuffling, and then there's 4 other machines or containers that do it in parallel, then 4 other containers that do it in parallel, and every time you shuffle. However, you might have noticed this is a bit inefficient there. Can we do that a bit more efficiently? Well, maybe yes. Maybe we can do it without the shuffling because then we can just do, maybe this is the filter and then the map and the flat map. We just continue with the same machine, right? Maybe there's no need to shuffle around. So in that case, squeezing them together as a single execution, and even, you know, sequentially, you can do all the way here and output the purple, then all the way here, output the purple. You see how that works sequentially, right? So this is optimized because then you don't need to shuffle, you don't need to ship it across machines, right? So this is an optimization that you can do to squeeze several transformations as if it were a single one, and then you can still do it nicely in parallel like that. So now this is called a stage, when you manage to squeeze together several transformations and do them, tie them together when you execute, right? So this is called a stage like this. However, it's not always possible to do that. When is it possible to do that? It's possible to do that if the dependency of your transformation is what is called narrow. It's basically when you have these vertical patterns in there. In that case, you are able to split it across machines and to squeeze it like this in stages. And in that case, here is the same diagram I drew earlier, except that now you have two transformations. I'm assuming these are narrow dependency transformations, which allows you to do them nicely, sequentially, and in parallel. Okay, so I just drew the same thing all over again, but with two transformations. Okay, I didn't cover yet the case where you have spaghetti there, because some of the transformations have spaghetti, right? So that I'll come back to you next week. But for the transformations that don't have a spaghetti and that are just narrow dependencies, nicely vertical, this here is how you execute. Sequentially within a task and across tasks, and in parallel across the cores, right? So multiple cores in one executor, all of that nicely in parallel. And you can control from the command line, if you execute your query, you can say, okay, give me 42 executors. So you say, okay, 42 of them. Then you can say 2 cores per executor. So this is how you get 2 and 2, right? 2 cores per executor. And you can also say, give me 5 gigabytes per executor, right? So 5 gigabytes is what every executor gets. And Yarn is going to take care of giving that to you. Okay, maybe I should stop here, right? I think I've showed you enough. And next week, I'll show you the wide dependencies, so the shuffling and the spaghetti when it goes across the machines. And we'll take it from there. Then we'll add Spark SQL on top, because it would be very tempting, of course, to do it. We'll have the data frames also that's going to come back as first citizen in Spark as well. So a lot of exciting things ahead. Do we have a question?
Yes. Can we use Yarn with Spark?
Yes, absolutely. This is actually all organized by Yarn, all of that. When you attribute the executors and cores and so on, these are actually Yarn containers. So a Spark executor is a Yarn container. You don't have to, though. If you don't like Yarn, you can use Spark with something else, with another resource management system, right? There are others. And there are also alternatives to Spark, right? There are also, I think it's called ETH is another alternative to Spark that works the same together with Yarn. So it's all modular. And if you don't like Yarn or you don't like Spark, there are other technologies that you can use instead, but they're more or less the same.
But Spark has no internal resource manager then?
There is still a Spark scheduler, right? That kind of also does some scheduling within Spark, but basically Yarn is typically used as the resource manager outside of Spark. All right. Okay. So it's 54. Let me just check that you followed just by asking you on you app, and then you'll be free to go. So let me share my screen. There. Just checking that you followed. And if you didn't, then you can ask questions during the week on Mattermost or next week in the Spark lecture. And of course, there's going to be plenty of practical exercises, as you can imagine. So you are going to be using PySpark in your Jupyter notebooks, and you'll be able to query data set. And you'll also have a practical exercise at the exam. So we'll give you data sets. And on the exam day, you're going to type PySpark queries in the Jupyter notebooks. So it's highly recommended that you take these exercises seriously, right? Because there will be PySpark at the exam. All right. So I hope I found a good balance between the theory and the practice, right? And you'll have the practice in the exercise session next week. All right, so thank you very much, everybody, for attending the lecture. As I said, no exercise session tomorrow and on Friday for those of you who want a repetition of the MapReduce exercise session. And then next week, you'll have exercise sessions again. Thank you, everybody. Thank you, Wenxi, for moderating this lecture, and enjoy your meal. Thank you very much. Goodbye.